in a level surface drag question, there's about 3 or 4 different ways this problem can be presented. I'm going to give you several of what I think are the question types and usually how they describe the problem and the setup for the problem. And I'm going to give you a couple ways to earn points. But ultimately, if you want to get an A on the next test, you will have to be able to solve one of these to its conclusion. But I will also tell you the stop points where, if you can do it at least up to this part, you'll get a B, stuff like that. So we're going to assume that there's a section of ground where there's no friction and then a section of ground where there's some kind of friction. And the green area represents the part where there's a frictional force of some kind. So these problems generally start on level ground. They're going to ask for probably a free body diagram for when the box hits the green surface. And almost always these problems will be broken up into 2 parts, with the first part being standard friction, where there's going to be some coefficient of kinetic friction. And that one's easy because that's going to have an acceleration that is constant. And because there's an acceleration that is constant, you can use Galileo's motion equations, or you just use F equals ma to derive an expression for the acceleration. And from there, you can usually figure out how far it goes, how long it takes to stop, stuff like that. These are very basic problems from the first semester. But then they'll go to part B, where they will change it up. And they'll say that there is a frictional force or a drag force or some kind of surface that intones a force that is proportional to the velocity. They may or may not put the negative sign in there. It's implied that this force is trying to stop the object. It's going to be in the opposite direction of the velocity. So the moment you know that, and these are, remember, velocity-dependent forces. This whole unit that we're talking about is going to be velocity-dependent forces. In all of these problems that have a velocity-dependent force, you cannot use your Galileo's motion equations anymore, because your acceleration affects the velocity, and therefore the velocity in turn affects the acceleration. So you're going to have to find a different way to solve them. And the only way that we're going to be trained on is solving a straightforward or maybe a less than straightforward differential equation. So usually the same kinds of rules will apply, meaning that they're going to ask for something like a free body diagram. So you should indulge them with a nice, straightforward free body diagram. I gave a test in AP Physics 1 last week. And in that test, so once you got your free body diagram, you're going to be asked, and this problem, they can ask it a couple of different ways. I'm giving you the phrasing, and there's a reason for it, because I want you to understand that they're going to give you a clue. So usually the clue is something like this: write an expression for a differential equation that could be used to solve for the velocity as a function of time. Write an expression as a differential equation that could be used to solve for the velocity as a function of time. So for some of you, that's going to be distracting, because you're not going to understand, what do you mean velocity? They're talking about something else here. They're talking about forces. You have to understand, the moment they say that, and they may not even say differential equation, but when they say that you need to solve and create an equation for the velocity as a function of time, you have to start with net force equals ma. So it's all you have when it comes to forces. And there are ways to get to velocity that aren't through differential equations, like energy. And so you can do the work energy function. But again, you have a force that is dependent on the velocity, so you can't actually calculate the work. Not using something like this. This is calculating the force as a function of displacement. You have nothing of the sort here. So you have to be careful, but they're going to give you the clue, and the clue is the word differential equation and expression for velocity as a function of time. Those are your clues that you're going to do this. They might even say in that thing, do not solve it. Fine, great. You're going to get points for just writing an equation down. You're not done quite yet, but we're almost there. First thing I want you to recognize is that you have to deal with the net force part, and you guys tend to forget these are vectors. So one of the first things you should do is make sure you are paying attention to direction. I would make your velocity the positive direction. I would make your velocity the positive direction and pay attention to the directions of your forces. By making the velocity the positive direction, you are making this force negative. And oftentimes there will be a negative in the equation as a clue that this force opposes the direction of motion. So when you write that in there, make sure you put in that negative sign. So the first part, of course, is just putting in your forces, whatever they happen to be. The second part is making it a differential equation. You have one substitution to make. So you write the differential form of acceleration. The moment you've done that, you've solved what they've asked for, or you've given them what they've asked for, right? But do not solve a differential equation that could be used to find the velocity as a function of time. That's this differential equation. Because right here, this says velocity as a function of time. It's right in the differential. Now, usually part B is now solve that equation. So we have to do the rest of it. Now, when they say solve the equation, oftentimes they will give you the answer, meaning they will tell you what the equation is supposed to look like. They don't care that you can derive it all the way. They care that you understand the process to get there. But often, if they give you the answer, that's because it's going to be used later in the problem. So if they give you the answer, you're not going to get a point for finding it. You're going to get a point for setting up everything you have to do to find it. Does that make sense? Now, if you want a C on your next test, you need to be able to set up the differential equation. All right, that's C-level work. It's a single substitution. But if you want a B on it, you need to get this all the way to something that can be integrated. So let's talk about the steps to do that. We've done this before, but I'm going to go back through the steps. We're going to use the process of splitting the derivative. We are not going to use the process of guessing at an answer, but we could. We did it once before, but this is a process and it works a little bit better. So we are going to split the derivative, and I'm going to go through each of the steps. You probably will only get 1 point for doing this whole process, getting it to the integral, but getting it to the integral is important. So here we go. Step 1. You want to isolate your derivative. You don't have to do this step. I like doing this step, though, because I think it makes future parts of this problem easier. So isolate your derivative. The next one is actually doing what the process says. You have to split the derivative, which simply means multiplying by whatever the denominator of this fraction is. So we're going to multiply both sides by dt. Again, this is the split part. Now, I'm trying to make this a little bit generic because there's no telling what differential equation you may actually have to solve. But this side has the t portion of the problem, and this side has the v portion of the problem. But whatever your derivative is, your next step is to collect terms. So whatever's on the derivative part on the left side, you need to get all of those variables there. So on the left side is a t, so you have to find every instance of t in your problem and make sure it's on the left side of the equation. There are no instances of t, so I don't have to worry about it. On the right side, it's dv. So you have to find every instant of v on the problem and get it to that side of the equation. So in this case, we're going to divide both sides by v. So collecting terms. Now, at this point, we're in a position to integrate both sides. And that simply means drawing your fancy little integral symbol. But you won't get points for just drawing the integral symbol until you do the next part, because we're setting up our integral here. And our next part is important. When you're setting up the integral, you have to, and a bunch of you are in calculus, and calculus is going to do this a little different than we are, although you can do it the way you were trained in calculus. I would like you to do it the way I'm suggesting for you, okay? In calculus, you would leave this probably as an indefinite integral. And when you do that, you will integrate both sides, and there'll be a constant that you'll add at the end of your integration because it's an indefinite integral, and then you'll put your boundary conditions in to figure out what that constant is. We will close our integrals and make them definite integrals by putting our boundary conditions in right now. The boundary conditions are almost always going to be your starting condition, whatever the starting condition was. So it's not hard to do this, but it's something that you have to be cognizant of. They will be looking for this. This is how you earn the point for setting up your integral. It's not by just drawing the s. It's about putting in your boundary conditions. And we have one. The first boundary condition is what you started at. We started at time 0 with a velocity of v naught. That's our boundary condition when we started. Now, keep in mind, if you did not make v the positive direction, you would have to make that negative v naught. That's why that's pretty late in the problem. A lot of people forget that, which is why I usually want you to deal with your vectors as soon as you can, so you don't have to worry about them later. Now the next step is you have to put your top conditions in. Your top conditions will be whatever this variable is. You just put that at the top, because we are creating an equation. So our top ones are going to be the variables of our problem. Now you just integrate each side. You actually do the calculus to get there. But if you can get to this point, you can set up your integral, then you're probably going to be able to get a B on our next test. Yep. Suggest. We'll take out the negative c over m, and that leaves us with the integral from 0 to t of dt. We'll just do one side at a time, all right? So let's do this part. When I take out the constant, I'm left with just dt in there. What is the antiderivative of nothing? Yeah, in this case, there's an implied t to the 0 power there. So I add 1 to that exponent and divide by the new exponent, and I'll just get t. So this is going to be c over m t evaluated from 0 to t. Well, evaluating this from 0 to t just means putting in the top boundary and subtracting the bottom boundary. So this is c over m times t minus 0. But I'm going to leave out the minus 0 if that's all right with you guys. All right. Let's do the right side. What's the antiderivative of 1 over v? If you don't know that, you have to memorize it, but it's also on your equation sheets if you don't. In fact, any integral that you will need for your exam will appear on your equation sheet. So if you need an integral and it doesn't fit this form, check your equation sheet. It's going to be on there somewhere. But we'll learn the process. This one is the natural log, so it's not tough. It's natural log of v evaluated from v naught to v. Now, you guys know rules for natural logs, but in case you don't, we're going to talk about them a little bit here. I'm going to go ahead and put in my actual variable here. You can't take the logarithm of a negative number, so that's why the bars are there, not parentheses. It's the way I was trained. You have to put that there, but we're dealing with physical quantities anyways. So generally, if you are doing something in physics and a negative has to appear there, you've made a you've made a mathematical mistake. You need to figure out where your mistake is, because you can't take the logarithm of a negative number. We need to solve this for v, and the log of v naught is a constant. We could do it right now, but it is almost always better if you have logarithms that are being subtracted to collect them. So I would always encourage you to collect them when you can, because you're going to get rid of that logarithm, and the only way to do so is to raise both sides of this to a base of e. So try and collect your logarithms if you can. It works out okay at the end, but most of you don't have good grasp of logarithm rules, so it's better if you can collect it and only have one thing to take the anti-log of. Raise to the base. So that is the calculus right to here. And again, the next part of this is algebra. It's not calculus, but we still don't have an answer yet that would be acceptable, and it definitely won't match the form of what's there on the test. So your next part is, of course, to get v isolated. So most of you who have had calculus know exactly what to do next. We raise both sides to a base of e. And then it's real easy. Just solve. Some things to keep in mind, though, once we get here. Check your units. Make sure it makes sense. So right now, if you have anything in an exponent like this, those units better cancel out to be nothing, because there should be no units up there. So that should be a unitless quantity. But we don't know what the units of c were. We could probably figure it out, because we know that it was a force that it was based on, and we multiplied c times the velocity, so we can probably figure out the units for c. But the important detail here is that when you take the exponential here, that's going to leave you with a unitless value. So the only units are those that are buried here. So that makes sense that we have v equals v naught times something, because that means we're going to have something that's in meters per second. The next thing, however, is, does it match up with your boundary condition? If you want to check your algebra, check your boundary condition. So our boundary condition is that our velocity was v naught at time equals 0. So put in time equals 0 and see if you get v naught. This is just checking to make sure your math works. So when I raise e to the 0 power, I get 1. And 1 times v naught is v naught, so it checks out. So I would always encourage you to check your boundary condition. That verifies your math. Now, they probably will have given you the answer, but there'll be more to it because they'll probably have other questions to ask about this. For example, does this thing ever actually stop? Technically, you guys would say no, right? But on an infinite time scale, it does. Now, we have this. There are other things you can figure out, and you should be aware of it. How far does the object go before it stops? That's an answer you should be able to ask because you have velocity. And the moment you have velocity, you also have a way of figuring out position. So keep in mind, you're not generally done just because you have an expression for the velocity, because you can now do it again to get an expression for position. In fact, try it. This should be one that you could be successful doing. Most of you know how to do this one. See if you can figure it out. Let's give it a try here. I'm going to split the derivative. I'm going to collect terms. I don't have to worry about that too much. They're already collected. I'm going to integrate both sides. I'm going to take the antiderivative of both sides, or integrate both sides, however you want to say that. Left side, I'm going to x minus 0. Right side, well, I'm going to u sub, which means I'm going to put u equals negative c over m a t. I'm going to take the derivative of that and find that du with respect to t is negative c over m. So dt equals negative m over c du. This is a standard thing called u substitution. I don't do it necessarily the standard way you're supposed to in calculus. So the only difference I do is I kind of strip away my boundary conditions while I do this, even though I'm not supposed to. I plug in all the things so I get something in terms of u. And again, if you have to take this integral, there will be an integral table that has this exact integral on it, not with c over m, but just some other constant. And you would plug in the constant. But we'll do this anyways. Pull out my constants, v naught, m, c, and a negative sign. And in my integral is e to the u du. What is the antiderivative of the exponential? Just the exponential. But I'm going to plug back in what I had for u, and I'm going to evaluate this from 0 to t. All right.